So let's start where we left off. We're looking at CFL condition. So this condition is very important. The simplest form. C is known as Courant number. Some constant into delta T by delta X. What is that constant depends from problem to problem. We'll look at these in more detail in much later classes. Right now, let's jump to transformations and grids. What are these transformations? What are grids? Okay, why do we need those transformations? How do they look like? These things we'll investigate right now. So when you say grids, we know that they are those select points which you want in space. We look only at regular grids in this course, rectangular grids rather. Okay. There are other types of grids called unstructured grids, which we won't go into detail right now. In this course, we won't go into detail. We know that there is something called unstructured grids which exist. And, it's similar to the grid points, but the details of generating them.
Sir,
And,
this is
yeah. Sharing,
yes.
I haven't shared. Okay. Are you able to see my screen now?
It's slow.
Tell me when you're able to see.
Yes. Yes, sir. Now it's
Okay. So we left off at CFL condition last class. So I'll just look at transformations and grids now. So uniform grids are grids which have constant delta x and delta y at all points. Okay. Remember all these, if you go back, all this, the difference equations are assuming constant delta x and constant delta t. Okay. That is when you write a difference equation, what does it say? There are I plus 1, I minus 1. Means delta x is same between I minus 1 and I and I plus 1. If they are different, then this is not correct. This is not a correct way of differencing. Correct? First, so this says that in order to apply these difference equations, your grid should be rectangular. That is, delta x should be constant, delta y should be constant. With that assumption, we are deriving the finite differences and hence the FDEs. Well, but for every problem, unfortunately, it is not possible to generate a rectangular grid. It is important that although even if you can generate, you will be making very gross approximations which will ruin your calculations. Okay? It is important that some grid points fall exactly on the body surface for you to enforce the boundary conditions properly. Suppose you want to say that these points is a body on the body, you want to enforce no mass flow rate through that fall, or you want to say that the normal component of velocity at that point is 0 to enforce the boundary conditions numerically. So if a rectangular grid is generated, it is difficult to ensure that the grid points always fall on the aerofoil or body surface. This shows an aerofoil around which somebody has chosen a rectangular grid. Okay. But some of the points fall inside the aerofoil, and on the aerofoil, exactly on the aerofoil, none of the points are there. So if you apply the boundary condition on these points, which is inside the airfoil, you will be probably solving a flow over a, some kind of solid like this. Okay, some kind of one, two, quadrilateral like this instead of an airfoil, which will give you very wrong. I mean, the error will be unacceptable in this case. This is a main issue with non-uniform grids. Sorry, uniform grids. Okay, so we are forced to choose a non-uniform grid. So a grid which is aligned to the flow direction and geometry would produce more accurate results. So in general, curvilinear grids are employed except very special cases. Okay, where the rectangular grid will make more sense. So the next slide, there's an example is shown. See, airfoil is there here. The points A and B are on the airfoil, and instead of X and Y, which is actually rectangular coordinate, X is in X direction, Y is in Y direction, you have Z and eta. Okay. So lines parallel to x-axis have y is equal to constant here. We call that as eta is equal to constant here. Okay. These are lines of constant eta. Okay. And lines parallel to z, parallel to y-axis have z is constant. So, have x is equal to constant. Similarly, here we have these lines are z is constant line. Then these curvilinear lines are eta is constant line. Sorry, I should say the curvilinear lines are the curved lines around the airfoil are eta is constant, whereas lines almost perpendicular to them are z is constant lines, almost orthogonal to these. So far, okay. So new coordinate lines z and eta are defined in such a way that the body or the airfoil surface becomes a line of eta is constant, or this becomes your new x-axis or z-axis. Then when z increases, you have these lines. Okay. Note that the grid points fall naturally on the surface. So all these points, okay, like A, B, then these 2 points and this point, all these fall on this eta is constant line. Eta is equal to 0 line. Or parallelly, if this is a z-axis, they all fall on the z-axis in this curvilinear coordinate system. So physical plane, it's a curvilinear coordinate. Now we use the term called physical plane. Physical plane means how it actually appears. Okay. Now we will transform this to a plane called computational plane. In this computational plane, instead of x-axis, you have z-axis. Instead of y-axis, you have eta-axis. Okay. In this here, the z varies from 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay. Here also z is varying between 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. Eta is varying from 0, 1, 2, 3, etc. Now you look at how these points corresponding to A, B, and C look like on the other axis, and on the other plane. So XY plane we call as physical plane. The Z eta plane we call as computational plane. So if you start from here, 0, 1, 2, 3, 4 is A. So here 0, 1, 2, 3, 4 is A. The next point is B. Here also the next point is B. Then from A you draw a straight line. This is C here. A dot and the next eta line is C. So is it clear how this is transformed into these coordinates? See, this is the initial one. Okay, this is the initial grid line. The next one, suppose you introduce a cut at this point. Okay, at this point you put a cut. I'm just showing it in a red line now, and you just open it up this way and that way, like tearing it apart, like Lord Narasimha tore open, the Hiranyakashipu's stomach. We are tearing it apart. Okay, so what happens? Next step is like this. The initial part of tearing apart. Next tail, you are tearing out further. Meanwhile, these lengths are not constant. They are like rubber bands. Okay, they can be compressed or extended. A small length may become larger. Larger length may become smaller in this when you do this transformation. Okay, they are elastic. Well, now you see, now this looks more like a rectangle, nearly like a rectangle. All these things. These red lines are very near this blue line. So you compress this whole thing into a very small line here, and you somehow adjust everything so that they become this rectangle finally. Okay, I'm showing the red lines here because they are almost coincident with the the last lines. So basically, I'm just diagrammatically I'm showing how physically they are changed. Remember, whatever calculations you do in this plane, the values at A, B, and C should be transformed back to the correct values at A, B, and C in the physical plane. Okay, every point. Otherwise, it's difficult. Now, why do you need this gory process, having it up, or opening it up? We call opening up the grid. Hmm? I just gave the answer some time back. Others, any idea? Why do you need this process? Others,
Yes, sir.
why do you need this thing to, make it rectangular?
Okay, sir.
See, we went into great lengths to make this curvilinear. First, we did a curvilinear grid in which the boundary points are falling on the airfoil, correct? And then we opened it up and made it rectangular. Why do we need to make it rectangular?
Sir, just discretize this whole thing into curvilinear. It will be a bit complicated, sir. So I think better if we just go with the rectangular.
Yeah, it's you're almost there, but not exactly. So, if you want to apply this FDEs, okay, the finite differences can be applied only on a rectangular grid, no, where delta x, delta y is uniform.
Yes, sir. Yes,
Mhm.
sir.
But in the grid shown, they are not uniform. Imagine delta x and delta y being adjacent point A, B. Say here, A and B, if you take delta x and delta y,
Yes, sir.
then you go to the next point B and the next point, the delta x is huge, delta y is very small compared to
Yeah.
this,
Yes, sir. Yes, sir.
right? So the delta x and delta y are not uniform in this grid when you go along this point.
Okay, sir.
But how does it look in here? Delta z is 1. delta eta is 1. 0, 1, 2, 3, 4. That's our indexing, no?
Yeah, yes, sir.
That index is actually z.
Z.
So delta z is 1. Y coordinate also. X 2 comma 1, 2 comma. This is 0 comma 0, 0 comma 1, 0 comma 2, 0 comma 3. Eta increases in steps of 1. Correct? So that is also there also your delta eta is 1. Here delta z is 1. Okay. Suppose we can solve the equation in this grid
Okay, sir.
and get the properties in ABC. We can transform it back to the other grid. Correct?
Yes, sir. We did.
Now, if you want to apply the wall boundary condition, if you apply at A, B, and all these points here, in this grid you will apply at A, B, and all these points here. Okay, the
Yes,
bottommost is a wall.
yes, sir.
So you should correspond the corresponding points. The corresponding coordinates in physical. You always mentally share a connection between the physical grid and the computational grid.
Okay, sir.
Should mentally share a connection. Should understand what's happening.
Okay,
Now
sir.
let's say there is one more problem now. What is the problem? Can you guess? Or shall I choose another? Yes, yes. Yes, yes. Swami Vasan, Naresh, no one here.
Sir, can you repeat the question?
Who is that?
Sir,
Ramanathan. Yeah, Ramanathan. See, there is one more problem. Now we have converted this curvilinear grid into a rectangular grid. Okay. You solve the
Okay, sir.
problem here. You can apply the FDEs. You can apply the finite difference equation because delta z and delta eta are constant here.
Yes,
They
sir.
were not
Yes.
constant in the physical plane. Correct?
Yes, sir.
One
Yes, sir.
problem solved, but there's one more problem remaining. What is it?
Sir, we have to transform.
Transform? You suddenly became silent. Not able to hear you. You have to transform? Okay, since you have grown silent,
Not go.
your mic has a problem. You are not able to hear you coherently.
Sir,
So, your mic has some problem. Your voice is breaking. Not able to hear you.
transform from
Wait. We'll
non-linear
ask.
to this linear.
No. Let me ask Naresh. Naresh is here. Sami Vasan. Hello. Anyone whose name I call is awake, please respond. Sami Vasan, Saptagiri Vasan, Sana, Sandita, Shyamla. Hmm. Who's responding? Hello, who spoke just now? Suvantan, Smish, Swaroop.
Yes, sir.
Smish. Can you guess what is the other problem? One problem is you have settled by transforming the curvilinear coordinate to a rectangular coordinate. Okay.
Yes,
But then what is the another problem remaining because of this transformation? What do you do by this? You are fitting the grids exactly onto the boundary. That problem is solved now. If you are solving the equations here, the finite difference equations are also uniform, delta z and delta eta. No, but what is the problem? No more problems remaining. What is that?
So we need to change the coordinates from.
Correct, correct. Need to change it. Very good, very good. Coordinate from x to z. So the governing equations are actually in x and y, correct?
Yes, sir.
All your, the momentum equation, your mass continuity equation, energy equation, are in x and y. Dou y by dou, dou u by dou x. It doesn't say dou u by dou eta. It doesn't say dou u by dou eta, dou z, correct?
Yes, sir.
And dou squared u by dou x, dou y squared. So you have to change all of that to z and eta. The whole equations have to be changed to this way. Okay. So,
Sir, which
yeah,
means you need a Jacobian to transform.
yeah, we are coming there. Exactly.
Yes, sir. So Ramanathan
Yes,
was
yes.
trying to say that he has put in a chat.
Oh, okay. Yeah. Jacobian. Exactly. Thanks. Good, Ramanathan. Yeah. Anyway, Smith got the point, main point. Main point is you have to transform. That's all. So, Jacobian will come in the next stage. The next is you bother out how to transform. Then you bother out Jacobian. Yeah, good, Ramanathan. Yeah. So, now the Jacobian, something we'll come to later. Yes. I got. Yes, physical plane is like this. Computational planes looks like this. Okay. So need for transformation. So the corresponding points A, B, C on the physical and computational planes are related. They are actually the same points. We are just visualizing it in a rectangular domain for our understanding. The physical plane is what is real. This is what exists. This computational plane, there is not a mystery because it's only in our imagination. It's there. We imagine because it helps us solve the equations. That is why we go to this computational plane. Okay. So the advantage is computational plane is rectangular with uniform spacing in the coordinate directions. So finite differences, as we discussed earlier, can be employed in the computational plane. But the governing PDEs are solved by a finite difference method in the computational plane. They are not solved in the physical plane because only in the computational plane you have delta z and delta eta constant. Now after that, you can translate it back to the physical plane via the corresponding points. So you solve for u at zeta is equal to 2, 1. The same u will be there physically at the corresponding physical point. Okay. But the governing equation, the problem is the governing equations must now be transformed to the computational plane. You can look upon z eta as the indexes, the indices you have. Suppose you have a point represented by 3, 2. Then z is 3 and eta is 2. Okay. So you can take them as the z eta variables. So at 3, 2, you will have an x, y. You will have a u, v, w, etc. Okay. So at 3, 2, for example, you have x is equal to 5.2, y is equal to 3.7. X, y may be 3.72. What did I say? 5.7 and 3.2. So the x at 3, 2 is 5.7. The y at 3, 2 is something, 3.2 or 2. Does this make sense? For example, the point C, let's say, this is 0, 1, 2, 3, 4, 1, 4, 1. Let's say the x at 4 comma 1. X is in XY direction. From this point, if you measure, probably X is, let's say 5 units. 5 units. Then Y is probably 3 units. Hmm? So the X at 5.2 and 3.1, let's say. So the X at this 0, 1, 2, 4 comma 1 is this 5.2 units. And the Y at the C, which is Y at 3 comma 4, the same number. The Y at 4 comma 1 is 3.2. So we have a corresponding X and Y for every Z and eta. Conversely, you can also say for this X, this is the eta. For any X here, the eta may be a fraction between these two, Z and eta. So for every Z and X, there is a X comma Y, which is easy to visualize. The inverse transformation. For every X comma Y, I say an X comma Y somewhere here. Okay. So at that X, I drop down a straight line and see what is the X there. Sorry, what is the Z there? 1, 2, 3, 4, 5, 6, 7, 7.5 or something. Here it is 1.5 or something, the Y. So 7.5, 1.5 is my Z, eta at that point. Although we don't draw lines at that 7.5 and 1.5, we draw that Z and eta lines only at constant intervals. Okay. Why? Because to make life easier for us. Nothing else. Okay. Now, so from xy variables, you have to transform the equation to z eta variables. So can write again, solve them here. This is the challenge. We look at very simple cases in this course, but you get the general idea. You can do the complicated ones yourself. That's all I'm going to cover in this course. Okay. You can probably go to the next slide. Now we'll go to some mathematics and get out of it. Okay. So not scary actually. If you understand what it means, it won't be scary. If you look at the equations as a whole, they'll be bewildering. Now consider an unsteady 2D flow with independent variables x, y, and t. X, y for 2 directions in space, and t for the time. If we look at the governing equations, we understand that we need a transformation derivative. First and second order transformations are needed because we get terms like u dou u by dou x, where dou u by dou x is a first order derivative. Then if you look at the viscous terms, it is mu into dou squared u by dou x squared plus dou squared u by dou y squared. So you need a transformation of second order terms. Sometimes you may need a mixed derivatives also. So we'll see how to calculate these derivatives. That is the next step. So z itself may be a function of time, x, y time. Let's consider the most general case. Eta may be a function of x, y, and time. And tau, let's say that the time in the transformed coordinate system. We call tau also as tau of time. Why are we considering tau? In case we are going to adaptive grids, then we will need this tau variable. Right now, we consider a very general term. We say we are considering adaptive grids also for this problem. So simply we put tau is equal to t, although we can have other transformations for t also. So the mathematics, the coefficients of dou by dou z, dou by dou eta, and dou by dou tau are actually okay below. So we look at the below one first. So dou by dou x is dou by dou zeta into dou zeta by dou x plus dou by dou eta into dou eta by dou x plus dou by dou tau into dou eta by dou t. Now dou eta by dou t is 0 because tau depends only on t. So that term is neglected here. Second term also is spatial. Dou by dou y is dou by dou z into dou z by dou y plus dou by dou eta into dou eta by dou y. The time term, okay, dou tau by dou y is 0 because tau is function only of t. Then we will say dou by dou t, again same thing, dou by dou z into dou z by dou t plus dou by dou eta into dou eta by dou t plus dou by dou tau into d tau by dt. Because tau is now a function of only one variable t, okay, d tau by dt is actually 1. So you can straight away say dou by dou tau. Well, this is the most general case. As usual, we'll simplify so that the headache becomes less. So in viscous flows, second order derivatives occur. So what we are telling is here, if you have dou by dou x terms, you have to substitute it with these terms. Dou by dou z and dou by dou eta is how they should look at in the transformed plane. For that you need this dou z by dou x and dou eta by dou x. Okay, these can be calculated. So you can write these equations in the transformed plane also. Now second order derivatives are there. How do you do that? A is equal to dou by dou x. So let's say A is dou by dou x, which is dou by dou z into dou z by dou x plus dou by dou eta and dou eta by dou x, as we have seen in the earlier page. Now dou squared by dou x squared is nothing but dou A by dou x. Again you put it as dou by dou z into dou A by dou z into dou z by dou x plus dou A by dou eta into dou eta by dou x. And in place of A, you substitute the right hand side here. Okay. A is nothing but this whole term. You apply it once more. Dou by dou x of A. Same thing you do. So that's how it will look like. Dou by dou x of this whole stuff, which is dou by dou z of this whole stuff by dou x plus dou by dou eta into this whole stuff by dou x. When you do that and you expand these terms and collect terms or whatever you do, you will get, instead of simplifying this, you will get more complications. Dou by dou z into dou squared z by dou x squared plus dou eta by dou x into dou squared by dou x dou eta plus dou by dou z into dou squared eta by dou x squared plus dou eta by dou squared dou x dou. Now these equations, this dou squared z by dou x squared can be computed from the your grid. Okay. Dou squared eta by dou x squared also can be computed. How eta vary with x, varies x. So you have only dou by dou eta and dou by dou z, which how the equation should look nicely in the computational domain. But these two terms pose a problem because you have dou squared by dou x dou z. Dou x is in the physical domain. Dou z is in the computational domain. Here also dou x is in the physical domain. Dou eta is in the computational domain. So we have to further simplify this b and c. Okay. So we don't want this this x here in the computational domain. We want only in terms of z and eta. We don't mind this dou eta by dou x and dou z by dou x. they can be computed numerically, that they don't pose a problem. See, this also can be computed. Dou squared eta by dou x squared and dou squared z by dou x squared also can be computed numerically. They also don't pose a big problem. But this one, where there's a mixture of coordinate system, dou square by dou x dou z and dou square by dou x dou eta, they form a problem. They will pose a problem. Okay. To differentiate a single variable. Now again we express this. What is this b? B is dou squared by dou x dou z. So we can express the dou by dou x of dou by dou z. Again, dou by dou x of anything can be expressed as dou by dou zeta and dou z into dou z by dou x plus dou by dou eta into dou eta by dou x. If you do that, you will get this equation for b. Now, dou z by dou x can be computed easily. Dou eta by dou x can also be computed easily. You get nice terms here, dou square by dou z squared and dou square dou eta dou z, which is okay. So we substitute, instead of b, we substitute this in this equation. Okay. Similarly for c, which is dou square by dou x dou eta, you will get this equation, okay, which we substitute here for c. Well, now if you do all these things, you will get an expression for dou squared by dou x squared. Wherever you have dou squared by dou x squared in the computational domain, you should use this very long expression. It is here. Dou squared is all this. So you see, the transformed equations get complicated. Then they act on u. So instead of the blank, you put u inside. Dou squared u by dou z squared, etc. Similarly, dou by dou y is this, and dou squared by dou y squared is this. I leave it to you as a homework, okay? Or maybe I give it as an assignment later. Do it as a homework. If you don't want assignments from me, do this as a homework. Most of the internals will be from the practical side, I think, which is, which Krishnan sir may be handling. So my the online portion will be from this theoretical part. By theory, I means both conceptual and mathematical. Now we have mixed rank second derivatives. Dou square by dou x dou y. You can put it like this. Dou by dou x is dou by dou y. Dou by dou y you call as dou d. Sorry. Yeah, d. Now that is dou by dou x of this whole thing is dou by dou y. So similar procedure you follow. You'll again get this b and c, same thing. You substitute the same b and c here. This b and c. You substitute here. You get this expression for mixed derivatives if you want. Okay. Any doubts in this so far? Here comes Raman's Jacobian. In many cases, the inverse transformation is easier to compute. Right? For example, instead of dou x by dou z, you can compute. Sorry, dou x by dou z may be easy to compute. Plus x2 minus x1 by zeta 2 minus zeta 1. So delta x will be your dou x by dou z. Dou x by dou y, y at j plus 1 minus y at j by delta y, or delta x, delta eta. Delta eta is just 1, so that becomes delta y. Delta z becomes 1, so that is just 1. It's much easier to compute those 1. So we can derive a relationship between the inverse transformation and this transformation. That's what is given here. Dou u by dou z is given in dou u by dou x into dou x by dou z plus dou u by dou y into dou y by dou z. Now just same thing in another form. The dou u by dou y, you are calculating dou u by dou z, dou u by dou eta, but same mathematics. Now here you solve for dou u by dou x and dou u by dou y now using Kramer's rule, dou u by dou x and dou u by dou y. Okay, and put it as a matrix and solve using Kramer's rule, or just solve it. Solve this for these two expressions. You will get dou u by dou x is this expression. Dou u by dou z, dou y by dou z. Dou u by dou eta, dou y by dou eta, the numerator. That is, the determinant of this is numerator. And denominator, instead of u and y, you'll have x. You have x and y. Okay. So J is known as Jacobian inverse transformation, which is the denominator here, dou u by dou x. So dou u by dou y will also have the same expression. Okay. So you will get this expressions, equation 1 and equation 2, which are for dou u by dou x and dou u by dou y. Okay. So completed. Any doubts? Akshay Nivasni, you find it easy to follow or difficult to follow?
It's okay, sir. I could understand at the end, but
Yes.
it's difficult.
Tell me the difficult part where you had problems.
When you were asking the question, I really did not understand what we were doing there.
Okay.
Only after that I saw.
Yeah, actually, that is actually a misleading question because I was asking about the future. I hadn't explained anything to you about that time. Just whether you can think forward and think something which missed out. But that's okay. That's not the issue. Even if I were a student and you were a teacher, I don't think I could have answered. Only people like Ramanathan or somebody, can probably, do that. Right, Ramanathan?
Sir, no, sir.
Why no? Why no? Yeah, they're good. There are many brilliant people in your class. In fact, most of the class is full of brilliant people. Okay. Shall we stop here today?
Yes, sir.
You want any makeup class after afternoon or is it okay? Enough for today.
So it's enough for today.
Okay, good.